Hello again, my dear students, and welcome to this second part with Class A output stage and power amplifier. In the previous part, we have demonstrated the basic schematic for the Class A power amplifiers, and we have determined together the conditions for a maximum swing related to the maximum capability of the current source invented using this BGT in a constant condition. Now, and as an application for that, let's start together discussing this question related to the power stage amplifier, Class A typically power stage amplifier. Okay. So first, let's start to read this question carefully and discuss together what is the main given of this question. For an emitter follower shown, VCC equals to 15 volt, VCE SAT is 0.2, and VBE is 0.7. And a constant and constant beta is very high. Find the value for R that will establish a biasing current sufficiently large to allow the largest output swing for an RL or load resistance of 1 kilo. Then determine the resulting output signal swing and the minimum and maximum emitter current for Q1. Okay, so basically the target of this design is to maximize that swing, and we already discussed this when we reach this equation, if you remember, my dear students. So simply speaking, you can, let's turn a bit to our whiteboard. So you can directly substitute in the equation, knowing that I times RL should be equals to VCC minus VCE SAT 2. So I think everything is given except I. So simply you can calculate I, that's I equals to 15 minus 0.2 over 1K, resulting with 14.8 milliampere. This is the direct substitution. But back to the question, you will find that the question is not to calculate the I. The question is to calculate the R, or the resistance that will lead to this I. Herein, we have to correlate this 14.8 milliampere with this resistance. Basically, from this graph, you can see that there is no direct correlation of that. What you can say is simply these pointers, let me open the pointer, sorry. Okay, so this point is negative 15 volts. So this point will be automatically higher with 0.7, which means that this current is negative 14.3 volts. So this is determined point or determined node in the circuit. But you know, or you already know that this is a ground. But here you still have two unknowns. You have the targeted unknown, which is R, and you have also another unknown, which is the current flowing in this resistor. As far as you are searching for R, so you have to know the I, or the current flowing in this branch, in order to calculate the R, or the resistance. And maybe this is the secret in this question. If you recognize well, my dear students, you will find that in this schematic, we have counted this die, which should be a forward die, because this point is 14.3, and negative 14.3, and this is negative 15, so the die is forward by. We have counted this die as if it's a transistor. We say Q1, Q2, and Q3. This is not a mistake, of course, by Sedgwick. it has some sort of a meaning here. This is related to what we can call, and I think you already have some background about it, which is the CMOS technology. In the CMOS technology, the main building unit is what's called a transistor. Mostly we are considering MOSFETs. However, in this high power application, we are considering BGT as well in our building units. So whenever you are going to build any type of a circuit, you have to use transistors as your building unit for that. Now, you would like to make a diode. So in order to integrate a diode in a CMOS technology, you have to integrate it in a form of a transistor. How can we do so? Let's turn back to the basics of a BGT. A BGT with a collector, base, and emitter is simply either an NPN or a PNP junction. In this case, as the arrow indicating the current is going to the emitter, which means that current is flowing from the collector to the emitter, if you remember the previous part. So simply this is N, this is P, and this is N. Now, if you concentrate on this schematic, you can see that this transistor is formed of two PN junctions. So we have the base collector junction and we have the base emitter junction. The base collector is a PN junction and the base emitter is another PN junction. What if we short circuit one of these two junctions by connecting the collector to the base? So simply, this PN junction is now short circuit. We basically know from our circuit classes that whenever you make a short circuit, you bypass anything in parallel. So now the remaining two terminal, now it's a two terminal device, not three terminal, because simply connect two of these three terminals. So the remaining two terminal of this device is simply a PN junction or a diode. And this is one of the very commonly used techniques to make a diode using a transistor technology. Herein, the VPE represents the current flowing in a diode and the I flowing. So you can write a very simple equation saying that I equals to I node, and sometimes we call it IS, saturation current, e to the power V over VT minus 1. Here, this V is simply VPE or VCE because simply VPE and VCE are the same now. And assuming a forward direction or a forward biasing, so this exponential results with a current which is much higher than the one. So you can simply write that I equal IS e to the power VPE over VT. If you remember, my dear students, this VT is the thermal voltage equals to KT over Q, which results of about 25.9 milli-electron volt, or millivolt, sorry, at room temperature. In another word, you can write also another equation by multiplying ln with these both sides of this equation. You can say that VPE equals VT ln I over I. You will use this equation somehow while you are considering some of our tutorial problem in next week at all. So this is simply how you consider a bipolar junction transistor as a diode by simply connecting or short circuit the base collector junction, keeping only the base emitter junction working. By the way, this does not impact the performance of a transistor simply because if you remember, my dear students, the first restriction for a transistor to work is to have a VPE equals to 0.7, which is again the same required restriction for a die to be forward biased. And now your VCE will simply be equal 0.7, which is still greater than VCE SAT, resulting that this transistor will work directly in the active mode. Okay, so this is what about the formation of a diode music transistor. Let's now return back to our circuit schematic, where we are searching for the role of this branch, including a diode and resistance, in the operation of our circuit. So I will just draw the bottom half of our circuit, including this negative VCC, and here we have a diode. So now I will plot this diode as a transistor. So this is simply how the circuit look like. So as you can see here, this is Q2 with V output, and this is Q3, which is our diode, and this is how the circuit looks like. So now our question is, we know the voltage of this point simply because this point is just 0.7 higher than the negative VCC. So simply this point is 14.3. But what about the current flowing here? We know the current here. This is the current we just calculated together. This is the 14.8 milliampere, if you remember. What about the current here? Okay, so very simply speaking, as you can see, we consider these two transistors, Q2 and Q3, what we call emitter transistors. Why we consider them the emitter transistor? Both have the same base, the base is common, connected together. Both have the same emitter voltage, negative VCC, and both are working in the active region. If you remember, we put a restriction here for this Q2 to be in the active region, and we told you that we have to go down with the voltage of the output up to VCC minus VCE SAT 2 to guarantee that this transistor is still in the active. And this will be our minimum output, if you remember, to have this point, the output equals to VCC minus VCE SAT. So as far as your output is minimum or greater than minimum, which is normal, this transistor will be active. And on the other hand, we just mentioned that this transistor also is active by force, because simply VPE here equals to VCE, and VPE equal 0.7, while VCE SAT equal 0.2. So simply VCE now, which is 0.7, is greater than the VCE SAT. So this transistor again is inactive. So both have the same base, both have the same emitter, both are inactive, so both are typical. So simply the current flowing here is typically equal to the current flowing here, which is still 14.8. Okay, maybe one of you will come with a question. Please consider that there is a node here. So simply speaking, if the transistor Q3 carrying a current called 14.8, but the current flowing in the resistance should be greater than this 14.8, because simply the current flowing in the resistance will split. Some of this current will go to the transistor Q3, and the other current will go to this branch, which including the base of both Q2 and Q3. which is of course correct. However, by returning back to the head of the question, where there is a note considering that for the transistor used in this circuit, that beta is very high. And if you remember your electronic classes, you will remember that IC equals beta times IB. Or in other words, IB equal IC over beta. So for very high beta, that means that the value of IB is extremely small, which makes you capable of assuming that this current flowing in this branch, which is the summation of the base currents in Q2 and Q3, is simply very, very low with respect to the current flowing here. That's why you can assume simply that the current flowing in the resistance is 14.8. Now you have everything. You know that this is a ground. You know that this is 14.3. And you know the value of the current flowing in the resistance. So simply speaking, the R you are searching for equals to 14.3 over 14.8. 14.3 is the voltage difference between this point and this point. Of course, this 14.3 is impossible because simply it's 0 minus 14.3. So the result is 14 positive 14.3 because simply the voltage is negative 14.3. I'm sorry for this. And 14.8 is a current. So by dividing this, you can get the resistance. I think it will be 0.9 something. And I don't exactly forget the second version. So this is simply how we can consider the R. And from this equation, my dear students, you can know that this R play a very important role in controlling this I. Herein, we make it in a reverse manner. We calculate the needed I, and then we return back to calculate the R needed to get this I. But whenever this R change, this I will change, and automatically this I will change. And this may clip your outstage amplifier. This is very important, my dear students. Okay, so let's turn back to our slides. We have still some part of the question which is not answered yet. I think that is the next part, the second part here. Determine the resulting output swing. I think we already know the swing. The swing will be from 14.8, which is VCC minus VCE SAT, to negative 14.8, which is negative VCC plus VCE to SAT. And the minimum and the maximum emitter current for Q1. So he is searching for this. Again, for a high beta, you can easily consider that IC is equal to IP. You already remember that, I think. So we need to know what is the maximum current here and what is the minimum current. And this is, by the way, will be part of our next phase in this lecture. Okay, so let's talk it very simple. We are controlling this current by controlling this point. This is the most critical point in this circuit, which is the V output point. So let's start considering the maximum of this point. What is the maximum of this? As we just mentioned, the maximum of this point is to reach VCC minus VCE SAT1, which is typically 14.8. In this case, what will happen, my dear students? In this case, what will happen is you will have here a voltage of 14.8, and you have here a 1 kilo ohm, which is this 1 kilo ohm resistance. So simply the current flowing here is 1 kilo ohm over 14.8, which is 14.8 milliampere. So the current flowing here, let me use an arrow. Here. So the current flowing here is simply this 14.8. And if you remember, my dear students, the circuit here, let me use this part of the circuit is a current source. So this part of the circuit has another current flowing. As far as this is a current source, so this current should be constant. And we just calculated this current, and we found that this current, which is flowing here, sorry, you have to change it to an arrow. I'm not a good user for Zoom, so I am sorry for that. This is correct. Okay, yeah. So the current flowing here, which is this purple current flowing in Q2, is again another 14.8. So this is another 14.8. So at a maximum condition, you have 14.8 milliampere flowing in the resistance RL. And you have 14.8 current in the current source, which is Q2. By a very simple KCL, you can see that the current flowing in Q1 is simply the calculation or the summation of these two currents, because simply this current, let's now open our laser. Okay. So this current reaches this point and then it's branching. Some of this current will go in this direction and the other will go here. So here we have 14.8 milliampere. Here we have 14.8 milliampere. So the total current flowing here at the maximum condition will be 2 times 14.8, which is 29.6 milliampere, or double the current flowing in the current source, whatever it is. This is a condition for maximum. What is a condition for minimum? Okay, for minimum, these points turn to be with its minimum value, which is negative 14.8. So if this point is negative 14.8 voltage, that means first speaking that your current direction will change. Your current will be flowing in this direction. That's right, because this is a ground and this is negative 14.8. So simply speaking, I'm not sure if you see the mouse, so I will repeat it. This is the ground and this is negative 14.8. So current flowing from ground to negative 14.8. So this is now the current flowing. What is the value of this current? Simply, it's 0 minus 14.8, which is positive 14.8 over 1 kilo, which is again a 14. I'm sorry. A 14.8 milliampere. So the current here is flowing, as you can see. Let me open the pointer again. So the current here is flowing from the ground to this node with 14.8 milliampere. Okay, what about the other branch? If we go to the other branch, this branch is still working as a current source with the same 14.8 milliampere. So that means basically that the whole current flowing in the load will go directly to flow in Q2. Resulting that this Q1 at this stage has 0 current, or basically it's turned off at this point. So the maximum current flowing in Q1 is 2 or double the current flowing in the current source, which is in our case 29.6 milliampere, and the minimum current flowing in this Q1 is typically 0. This is, I think, all we need to answer this important question. Now, let's turn to another point. using the same circuit. Let's investigate together 4 points on this circuit. What are these 4 points? The first is this point, which is this V output. The second is this voltage drop, or what we can call V E1. The third is the current flowing here, or what we can call IC, or IC1. And the fourth is the power consumed in this Q1. Let's try together now to make a plot showing the sinusoidal variation of these 4 points. Herein, I would suggest to work with my PowerPoint from one hand, and in the other to have the circuit demonstrated in front of you, either using your mobile or even to split your screen into 2 windows or whatever, as you want. So I will turn now to my whiteboard to demonstrate these 4 points. So the first point is the V output. I think this point we already have demonstrated well before, saying that the maximum variation on this point, which is the V output point, is something like that, from VCC minus VCE sat to negative VCC plus VCE sat. I think we do it more than one here, this variation. But in this stage, Cedra tried to make life more simple and told us, let's assume that this VCC is much greater than VCC sat. So we can simply say that, okay, this variation is from negative VCC to VCC. And this is just an approximation to make life easy mathematically and in form of representation. So our first point is, let's assume that the output is something like that, from VCC to negative VCC. Let's now try to discuss the second. This is the output. Let's now try to discuss the second part, which is VCE1. What about VCE1? Back to our schematic. Okay, what is VCE1? Simply speaking, VCE1 is VCC minus the output. So it is just, VCC is a constant. We just plotted together the output. So this is just a subtraction of a curve. Let's do it in us. So VCE1 is VCC minus the output. So when the output is equal to 0, then VCC minus 0 is simply VCC. When the output equals to VCC, then the output is VCC minus VCC, which is equals to 0. Again, 0 with a VCC. And finally, when the output is equal to negative VCC, then VCE1 will be VCC minus turns to plus VCC, results with 2 VCC. So you have something like that. This signal, as you can see, my dear students, is floating between 0 and 2 VCC. This is how VCE1 looks like. Now, let's turn to IC. Let's turn together to IC. So let's turn to the third item, which is the current flowing in the Q1, the IC. As I mentioned, IC and IE are typically the same, assuming that beta is very high, which is already stated in the head of the question. So now we just do the same process. If you remember, my dear students, few minutes maybe or seconds ago, when we estimated together the current flowing here. Just going to, yeah, when we estimated the current flowing here. So we say that when this is maximum, this current is typically 2I, where I is of current flowing in the diode. And when this is minimum, this current is 0. So let's do it here. When the output is maximum, as you can see, my dear students, so this is 2I. And when this is minimum, this is 0. So you have an output current curve looks like that, varying from I to 0 with an average I. So this is the case for the current flowing in the transistor and the voltage across the transistor. Why we are interested in these two graphs, my dear students? This is simply because the power consumed in this Q1 is the multiplication of these two graphs. So the force parameter, which is the power, can be easily found by multiplying this two graphs, as you can see here. So if you multiply this voltage with this current, you will get the power. So as you can see, now the average of VCC times I, so this is VCCI. Now, when this current is maximum, please take care, the voltage is minimum, so this is 0. And when this voltage is maximum, the current is minimum, so another 0. So you have a power flowing like that with the maximum VCCI. Let's do it in a better representation using the slides rather than my very ugly plots. So this is the output, as you can see. Here, this is the power consumed in the transistor. Why we are interested in this power? This is simply because, my dear students, the power consumed here is considered as a lossless power. Please remember that your target that all the power delivered in this stage should go to the load. Any power consumed in the transistor is simply considered as a lossless. So this power consumed in Q1 is simply considered as a lossless. That's why, in order to calculate the efficiency of this stage, what you should do is you should divide the power reaching the load, which represent the maximum power, or sorry, which represents the targeted power, over the whole power you consume in your circuit. Just take care, my dear student, that the power consumed is a DC power, which is simply the power consumed by these two batteries, VCC and negative VCC. This negative VCC consumes I, and this VCC consumes I, so simply it's 2 VCCI. However, the power reaching the load in it is an AC power. That's why we are going to calculate it like that. If you remember this rule, it's V output over root 2, V output maximum over root 2 square over RL, which is half V output square over RL. And as I just mentioned, the power of the supply is simply 2 VCCI. So the overall efficiency of our power amplifier is 1/4 V output over IRL times V output over VCC. Now, if you see this relation, my dear students, you can estimate the maximum efficiency of this stage, because the maximum value of this V output, let's return back, is VCC. So if we substitute here by VCC, and I times RL is still VCC, so this is 1 and this is 1, So the maximum efficiency of this stage is only 25%. Only 25% of the power you deliver using your DC voltage is, or your DC supplies, is converted to the load. And 75% of the power is consumed in the transistors. That's consider the main disadvantage of this output stage class A power amplifiers. Before leaving this class A and terminating this part, please, it's very important for you, my dear students, to investigate a very important point, which is we implemented these power stage amplifiers seeking for first minimum output resistance. So when you do this circuit using your multi-sum or your cadence in the project, please try to investigate what is the value for the output resistance of this structure so that you can verify, is it really useful as an output stage power amplifier or not? That's all for this class A power amplifiers. The next lecture will be with class B power amplifiers. Thank you very much and see you later on.